Methyl. So, the floor is yours.
Okay, so my project was the photolysis of methyl iodide, otherwise known as iodomethane. So why investigate methyl iodide in the first place? So in organic chemistry, it is known to be the carbon of the methyl iodide is susceptible to a nucleophilic attack, and iodine is also a strong leaving group, so it's really easy to methylate products using this molecule. And then also it's very small, so it's slightly easier to demonstrate in MATLAB. So the products are easier to interpret than a triatomic model. So ethane, ethyl iodide would be significantly more complicated than methyl iodide. So that's part of the reason why we chose this. So what my simulations model is pump probe spectroscopy. So it's a 1 femtosecond pulse that splits into two sub-pulses. One pulse is the pump, which excites the electron, and the other one is the probe, which detects it. And then, so the pulse is significantly shorter than the relaxation of it, so you can excite the electron without having it interfere with the relaxation of the electron. So that is also the reason we investigate it. And different things that you can change are that the configuration the configurations that you can change are the amplitude, the phase, the polarization, and the frequency. So those are just things that you can tweak to make it exactly the way you want to detect it. So after it excites, it relaxes into two different spin states. So the spin 1/2 and the spin 3/4. Spin 1/2 has a higher energy than the spin 3/4 does. And in literature, they're denoted as the I star is the spin 1/2, and then the regular I is the spin 3/2. And so the higher energy is seen here, and these are just the labels for the potential energy surfaces that we investigated. And this is the reaction barrier for just the breaking of the methyl iodide. So I'm not going to get into methodology, but it's all here. Okay, well, this is the initial wave function. So it has a few different components to it. So I don't know how in depth to go, but we have the Hamiltonian, the actual equation for the initial wave function, the potential energy surface calculations, as well as how I converted the temperature in relation to momentum. So here are my videos, that's the word. So this is the excited electron, and the electron is relaxing. This red here is the overall probability of the electron to be in the two different potential energy surfaces. And then these little humps here are the wave packets propagating as a function of the bond between the iodine and the carbon. So as you can see, and this is temperature 0 with a momentum of 0. So as you can see, as it propagates, the bottom one, which is the spin 3/2, propagates significantly faster than the one on the top.
Again, it's too many lines on this graph. So you have 3 different types of potential. So what is it?
Yeah.
The green lines. I mean, green lines, which looks like a potential.
Yeah, there's two different. There's a. Okay, so it's a. So there's these two here are relaxed to the same state, whereas there's only one state here. And off the top of my head, I can't tell you. There's but it's in my report. I can't remember right now though. There's different ways to get to that state. So there's I think it's I can tell you, but it relaxes into two different states. So this state and this state, they both relax in the same way.
But where's your potential?
Can you show it on equations? In your slide with equations, there are potentials like V of x.
Are you talking about this?
Yes. Can you explain what's the difference between V sub 0, V sub 1, V sub 2, V sub 3?
Oh, so this is 3 lines based on these terms. 4 coming? 4.
Can you just briefly comment what's the difference of this V0, V1, V2, V3, and how it relates to the question of Professor Patnode.
Wouldn't it be the well depth? So the variations in the well depth would be what causes it to relax differently. I mean, that's...
Yes, but you may highlight that there are 4 different potentials.
Oh, well, yeah, here.
And those 4 different potentials is what you are showing.
Yeah. Yeah, well, yeah.
But what's the difference between them? Why do you need 4 different potentials?
Because they relax in different manners. There's one that's like a horizontal, I think that's what it's called, a transition. And then there's one that's, I can't remember. It would really help if I could remember the word right now. But there's different types of relaxation. So there's one that...
conservative and dissociated, or something different?
No, it's different. Sure, I can't remember it. But it relaxes in different manners. So there's just the 3 different lines, and then they end up at different spin states.
Mm-hmm.
So different products that are similar in energy.
Yeah, basically. So 2 of them result in the same energy, and then 1 of them results in a different one. So there's 3 lines. The 4th line, I'm not sure what you're talking about. This is the electron. These are the 2 probabilities. So the black and the green are the probabilities. This is the overall distribution, and these are the 3 lines that we're talking about. This is the non-excited state. I guess so. There's no, since it's excited, there's no electrons on this non-probability. Yeah. Okay. Well, we'll continue. So the second one is a temperature of negative 194 degrees Celsius. So the initial P0 that I chose was 10. And so as you can see, it's starting to get a little bit closer for the distribution as it's propagating. They start to get similar and similar. I'm not going to let this go to the end because we have a time limit. So as the temperature increases, they become more and more similar, basically mimicking each other, but the distribution remains the same. And I thought that was weird, so we investigated it further. So this time up here is a little off, so it's actually going from 0 to further rather than from negative to nothing, because it was simulated differently previously. So if we let the temperature oscillate the molecule beforehand, when it eventually will excite, the probability distribution will vary differently than it did at the same temperature previously. So yeah, this one's a little bit longer. So this is the same simulation, except for this one was isolating previously. So you can see that it's very different looking than what it was here, where this one had nice lines. This one has very different, oscillating features to it, and they propagate at roughly the similar time, but still a little different. So if I were to do this further, I would allow it to oscillate previous to the excitation to allow it to actually simulate the molecule correctly. So, anyways, my conclusions were temperature increases the rate at which the I star state propagates, and then the propagation ratio varies if it's allowed to oscillate before it's excited. So. That's it.
Okay, let's thank Alyssa. So, any questions?